All right, this is lecture 3 of Computing 307, section D1, the beginning of complexity of algorithms. For this section, Kleinberg and Tardis chapter 2, sections 2.1, 2.2, and 2.4 are required readings. So I'll give you readings with every lecture video. And those readings often will be very helpful to you in preparing to do problems or tests. When I say it's required reading, I mean there might be things on there that I assume that you have read, even if they don't directly appear in the lectures. So when I write test questions, I assume that you have read the sections that I say are required. Okay, when we talk about analyzing an algorithm, there's all kinds of things we can analyze. We could study it for correctness, try to prove correctness, or prove that it's not correct for that matter. We could analyze properties of its outputs. For example, in the Gale-Shapley, we saw that the solutions it produces are not only correct, but they're very special ones. They have certain properties which you might consider desirable or undesirable depending on the application context. Okay, and we might analyze the complexity. And most of the time when people say analysis of algorithms, that's what they're primarily talking about. And by complexity of an algorithm, we mean the amount of some computational resource that it's used. And usually this is time or sometimes space. It can be other things, communication, number of bits communicated, for example, or other things, but usually time and space. And time is abstracted, so it's not real time, because the real time taken by an algorithm would depend on the implementation, the hardware, many other things. Okay, so time is measured by the number of some category of primitive computational steps, and space as an amount of memory, number of bits of memory required for executing the algorithm. Thinking about the complexity of algorithms is about as far from new as you can get and still be talking about algorithms. So algorithms abstractly have been around a long time, but the idea that they would be mechanically computed is not quite as old. The first design of a machine that's a universal computational machine, can compute every computable function, as far as I know, was by Charles Babbage, a thing he called his analytic engine. And he said as soon as an analytic engine exists, he never managed to actually complete building one, it will necessarily guide the future course of the science. Whenever any result is sought by its aid, the question will arise, by what course of calculation can these results be arrived at by the machine in the shortest time? Okay, in other words, what's the complexity of the algorithm that you implement with the machine? Okay, so even he is not talking about actual time. I mean, he means the implication for actual time, but he means how many times do you have to turn the crank on his machine, right? And you would, of course, like to minimize that. And that's what we're focusing on a lot when we study complexity of algorithms. We want efficient algorithms. We want the algorithms that use as little time and space as possible. But of course, not all problems are equally difficult. So as little time and space as possible for the problem being solved by the algorithm. So this brings us to this idea about some problems being harder than others. So tractable problems are what we call problems that have efficient algorithms. By intractable problems, we mean problems for which there are no efficient algorithms. And this distinction is interesting and useful. And unfortunately, there's a lot of problems that we sometimes call them apparently intractable. These have the property that they, as far as we can tell, they're intractable. Nobody can find a general efficient algorithm for them, but we can't prove it. So we can't prove they're intractable. It just seems like they are, even though lots of people have tried to prove that they are or to prove that they're not. Okay, so this is a fine idea, but it's a little vague because we haven't talked about what counts as efficient. And there's actually no real, say, unqualified way to define efficient algorithm because algorithms are complex and the problems they operate on complex. So let me motivate a distinction with an example. So we've studied the stable matching problem, and we have a pretty nice algorithm for it, the Gale-Shapley algorithm. Let's consider a second algorithm. I'll just call it algorithm A. Okay, and what we do with that algorithm is we generate all the perfect matchings for our input. Okay, and then for each one, we check if it's a stable matching or not. Okay, and we stop in output one when we find one, or we, right? Okay. So now this is a pretty different algorithm, but it's a pretty simple problem. So then they're both fairly simple algorithms. So it could be that's for small n, when the number of hospital institutes is very small, the Gale-Shapley algorithm, this algorithm might take similar amount of time, or you know, they're simple algorithms. So it might be just that they're so fast you don't even care about the difference in time, right? But suppose that n is large, let's say 10 to the 6. So 10 to the 6 is a million. You might say, well, there aren't a million hospitals in the world. And that's true, there aren't. And so maybe we don't care if it's hospitals. There are lots and lots of other applications of stable matching and very closely related problems. So we might actually care. 10 to the 6 is not very big for many kinds of settings. I did look it up. There's about 6,000 hospitals in the US, about 10,000 in Europe, broadly construed, and about 150, 160,000 in the world. So that's already a pretty big number if you were taking into account all hospitals. It's a surprisingly large number, but it's not a million. But anyway, let's suppose we have an application with something like a million. So what's the time for algorithm A? Well, it's n squared. So to generate all perfect matchings, there's n factorial perfect matching. So at least n factorial steps to generate them, and about n squared steps to test each for stability, right? We have to, intuitively, we probably have to look at each student and hospital pair and see if that's an unstable pair or not. Okay, so we expect something like n squared times n factorial steps. Okay, if we plug in 10 to the 6, we get this something actually much bigger than this very nice number, 10 to the 1 million. So that's 10 with a million zeros after it. Okay, that's a ridiculously large number. We might as well consider this, it'll take forever for all intents and purposes. I don't think even the most optimistic notions of what computational machinery we might have in the next century would be going that far, or at least say the next few decades. Anyway, on the other hand, the time for the Gale-Shapley is about n squared proposals. That's about 10 to the 12. And I don't even need to code it and run it. I can do if I know just a little bit about about the algorithm implementation and about how efficient processors work, I can actually figure out that I can easily code this up so it'll run in less than an hour on a current desktop computer. Okay, so forever versus an hour is a pretty big difference. And I think even if we pick the real setting of 6,000 US hospitals and probably 20 or 30,000 residents, that's already you'd already be in a major distinction between those two algorithms. So this is to illustrate this kind of intuitive distinction between exponential time complexity and polynomial time complexity, right? So we think of an algorithm that's exponential time as being not efficient, and a problem being intractable if the only algorithms we know for it are exponential, require at least exponential time. And an algorithm we consider efficient if it's polynomial time, and a problem we consider tractable if it has a polynomial time algorithm. Okay, now this is not a perfect distinction, but it's one that theoreticians and in general in analysis of algorithms, we take as kind of a rule of thumb distinction. So consider efficient as polytime or tractable. And why is it imperfect? Well, because there are polytime problems that seem hard. Okay. And there are polytime algorithms that are impractical. Okay, so for example, here's one. This is a paper, I haven't read the paper, but it gives a polynomial time algorithm that's n to the 120. So that's a ridiculously large exponent. It's probably not going to be of any use unless n is always going to be smaller than 10 or something, pretty small. And there's other algorithms which have small exponents, okay, but astronomically large constants in front of them. So the big O is big O. It's big O of n, right? But the big O is hiding an astronomically large constant. And so an implementation, if a general implementation can't really get around this, you can't really use it. Okay. And thirdly, although exponential time is bad, there are actually quite a few exponential time algorithms that are useful in practice. This includes exponential time algorithms for problems that have polytime solutions, like linear programming, has polytime algorithms, but sometimes the exponential time simplex algorithm is actually better. And also there are lots of problems which are intractable or apparently intractable, for which our only algorithms are algorithms that require exponential time in the worst case. But we've managed to actually come up with ways to implement them that are useful in the real world. And there are applications with software that people run every day in certain disciplines where they're running exponential time algorithms and getting answers. And which doesn't mean the problems are easy. It means they're easy enough to do some useful work. Okay, so it's not perfect, but it's useful heuristically. Why? Because most of the time, and you're faced with a natural problem, and it turns out to be a polytime problem, it usually turns out to have a reasonable low degree polynomial time algorithm, right? So there are exceptions, but they're exceptions. It's not the usual experience. And the second thing is that most problems that don't have polytime algorithms or are not known to have polytime algorithms do seem to be genuinely hard in practice. So I talked about, so there are problems that we only have exponential time algorithms for. And people really run those algorithms in practice and get solutions. But it's always, it's usually very tricky if you make the instances slightly bigger. Often they become too hard. You have to wait for next year's computer or next year's improvement to the solving software. And they're very sensitive to the inputs. So there can be applications where the inputs are all pretty nice and things look okay, but others where sometimes the input is okay, you get an answer, and sometimes it's just going to run and run and run and run, and you just have to give up and do something else. Okay, so since this is mostly a theory course, we're going to regard polynomial time as efficient or tractable. So let's think about this distinction a little bit. I just want to emphasize the polynomial and exponential time are qualitatively very different. Okay. Certainly mathematically. So polytime means we have time that's running, that's something like c times n to the d for positive constant c and a constant d bigger than 1, or at least 1, right? Right, n is always the input size. Okay, unless we say otherwise. So what happens when your complexity is a function of that form? Well, when you double the input size, the time it takes to get a solution is multiplied by a constant. So it gets bigger, but only bigger by some constant multiple, right? So we can just take our c times n to the d, and we can plug in 2n to see what happens when we double the size. And what we get is 2 to the d times c times n to the d, okay? In other words, we increase the time by a factor of 2 to the d. That's a constant because d is a constant. Okay, so it might be a big constant, but it's still a constant. So this is kind of reasonable. If you just think a linear time algorithm, right? Of course, d is 1 in that case. 2 to the 1 is 2. You double the input size, you take twice as long to solve it, right? That's intuitively what should happen. On the other hand, if you have exponential time, which one way to write it is we have time proportional to r to the n for some constant r that's bigger than 1. Okay, in many settings it's 2, but it can be many other things. What happens when we double the input size? Well, let's take r to the n and we'll plug 2n in place of n. We get r to the n squared. Okay, so what happened is that we double the input size and the solving time squared. Okay, so that's much faster growth, right? And so if we think about asymptotic notation, well, for every r bigger than 1 and d bigger than 1, n to the d is big O of r to the n, and r to the n is not big O of n to the d. Okay, so these are very different things, right? For any choice of r and d. Okay, so the smallest exponential and the biggest polynomial you can think of still have the property that the exponential grows much, much faster than the polynomial, at least asymptotically. Every exponential grows faster than any polynomial. Okay, so what are we going to do in this course? We're going to do two main things. Okay, for the first probably 2/3, 3/4, we're going to go through several algorithm design techniques or schemata or algorithmic approaches, okay, that are often used to create polytime algorithms for tractable problems. Okay, and the second thing we're going to do is try to understand and ways to, understand ways to understand and approach intractable problems or apparently intractable problems. Okay. Now I've already used the big O because I assume that you've seen it before, but we still need to do probably some review and some practice before we get into the more interesting bits. Okay, so big O is a notation for describing upper bounds on growth of functions. Okay, so hopefully this is a reminder. Everyone here should have seen this a few times, but it doesn't hurt to be reminded. So we say f of n is big O of g of n if there are two positive constants, traditionally called c and n naught, such that f of n is less than or equal to c times g of n whenever n is bigger than n naught. Okay, notice that the definition doesn't say anything about algorithms, right? This is about functions, not about algorithms. Sometimes students get confused because of that, right? It's a way to describe functions right? You get to choose which function you're describing, right? Which may or may not have anything to do with an algorithm or any particular property of an algorithm. Okay, so let's do a little example. Suppose f of n is 32n squared plus 17n plus 1. We claim that f of n is big O of n squared, and that it's neither big O of n nor big O of n log n. Okay, before we prove them, let me just visit this little picture here. Okay, the idea of this is that here's our function f of n, and that some constant times g of n is an upper bound, right? This is g of n. And they go off to infinity, and c times g of n is always bigger than the f of n. Well, we might excuse some lower, for some finite number of small values of n. We might forgive f for being bigger than c times g of n. We can just ignore that, and that's how we pick the n naught. So as long as n is bigger than n naught, c times g of n is upper bound, right? For f of n, it's at least as big as f of n. Okay, so g itself might not be an upper bound for f. This is a candidate for maybe this is g, right? But when we multiply g by some constant, bigger than 1 in this case, we get an upper bound for f. Okay, so let's look at these two claims. F of n is big O of n squared. Why? Well, f of n is 32n squared plus 17n plus 1. This is, at most, 32n squared plus 17n squared plus 1n squared, provided n is at least 1. Okay, why did I do that? Well, so I can collect like terms, right? So this is less than or equal to 50n squared, provided n is at least 1. Okay, and so this is basically plugs into the definition, right? Set c to 50 and n naught to 1. Okay, and you satisfy the definition. Okay, f of n is not big O of n or big O of n log n. I'm just going to do the one of them. Okay, so what does it mean? That's the claim that there are no constants c and n naught bigger than 0, such that f of n is less than or equal to c times n for all n bigger than n naught. Right? Okay, suppose the contrary of the claim that there are such constants. Okay, then if there are such constants, we can choose some such that 32n squared plus 17n plus 1 is less than or equal to c times n for every n larger than n naught. So to show that it's not the case by contradiction, I'll choose a value for n, okay, based on my choice of c and n naught. Okay, so I would choose, I'm going to let n be the maximum of c and n naught plus 1. And then what do I find? I find that 32n squared plus 17n plus 1 is at least n squared. It's bigger than n, which n squared, which is bigger than c times n. Okay, contradiction. Okay, now when we go to apply big O to discussions of algorithms, we say all the time things like this: algorithm A is big O of f of n. This is really sloppy, right? Because algorithm A isn't a function, so it can't be big O of f of n. Usually, but most of the time we're talking about certain properties of algorithms, right? So usually this statement is short for the worst case running time of algorithm A is big O of f of n, okay, which in turn is short for a more careful statement, right? If we let t of n be the maximum number of steps that algorithm takes on any input of size at most n, then t of n is big O of f of n. That's the statement of that's what we're really claiming when we say, usually when we say this. Okay, that's the default interpretation of that statement. Okay, so reminder, it's just the last slide. Maybe you don't need it, but t of n is big O of f of n means there are positive constants c and n naught such that if n is bigger than n naught, t of n is less than or equal to c times f of n. Less formally, we might say for all sufficiently large n, T of n is less than or equal to C times F of n. Or we might say for all but finitely many small values of n, T of n is less than or equal to C times n, right? These small values might not be actually small by any reasonable notion, but they're small relative to n getting arbitrarily large. We're talking asymptotically, we're talking about in the limit, right? So any particular value is small compared to what happens to n as it goes to infinity, right? The limit. Okay, or, so this is maybe the nice way to say it, T is asymptotically upper bounded by F. Okay, that's the nice way to compactly say that without saying something mathematically meaningless. Okay, so quick example. Gale-Shapley, oh, isn't that nice? Gale-Shapley. So people often read this name as wrong as Gale-Shapley. It's Gale-Shapley. Sometimes it's easy to write it wrong too without noticing. Okay, so Gale-Shapley, what's the input? The input is preference list for K hospitals and K students. Okay, so I changed my variable there from N to K because N normally is the input size, but the number of hospitals and students isn't the input size for Gale-Shapley. Right? The input size is K squared, actually 2K squared, right? Because each hospital has a list of K students, preferences for K students, and each student has a list of length K giving their preferences for hospitals, okay? So the input size is actually, I'll just look at, it's 2K squared. Okay, so complexity analysis. Well, we have at most K squared, which is N iterations of the main loop. And each iteration of the main loop takes big O of one time. Well, so one of the things we did in that lecture is we went through the operations in the main loop and we verified that if we chose the data structure appropriately, we could execute each of those in big O of one time. So the whole body takes big O of one time, right? Okay, so the total time I claim is big O of n. Right? So Gale-Shapley is actually a linear time algorithm, even though people write that it's n squared, right? Because we find it natural to say it's big O of k squared because we think of the instance size in terms of number of hospitals and students. And that's not actually the input size, right? But that's how we talk about it. Nobody would, you say to somebody says, how big is your stable matching instance? And you would say 100 hospitals and 100 students. You wouldn't say size 200,000 numbers unless somebody asked you, kind of in a more fussy way. Okay, now just before we move on, I did something here, right? I took this step. N iterations with big O of one time is big O of n. That sounds intuitively reasonable. It's big O of n. But mathematically, what happened? I used a fact that I would write this way. N times big O of 1 equals big O of n. Okay, but this should give you pause, okay? Because this is a number, right? This is not a number. And so what does it even mean that I'm multiplying them together? I'm multiplying a number by a thing that's not a number. That's not multiplication in normal sense, right? And this equality is not equality, right? I'm not saying that this thing and this thing are the same. So usually if I write f of n is big O of n, I have to find out what that means, right? But again, this thing on the left here, this is not even a function. So what does it mean to say it's big O of n? Okay, and we do this kind of thing all the time when we're doing complexity analysis, because if we didn't, we would never get anything done. So let me clarify what it means as an example so that when we do, if we do lots of these things in the future, you can easily see that it's not, that they're meaningful mathematically meaningful and not nonsense. Okay, so what would it mean if I wrote or said this? Well, you can think of it as meaning this, that if f of n is n times g of n, and g of n is big O of 1, then f of n is big O of n. Okay, and this is a true statement. That's right. Everything here is mathematically meaningful. Okay, and I can prove it, right? So if g of n is big O of 1, then there are these two constants, right, such that g of n is no bigger than c, okay, for all large values of n. Okay, so now f of n is n times g of n. So f of n is less than or equal to n times g of n, of course. And now I can just plug in this property of g of n that I just proved above, right? Namely, that it's no bigger than c whenever n is bigger than n naught, right? So it follows that f of n is no bigger than n times c, okay, for every n bigger than n naught. And that's just the definition of f of n being big O of n. Okay, I would just reverse the order of the c and the n, but okay. What's going on? Okay, we'll go do a few more examples of basic big O statements. Okay, so we claim a0 times a1 to the n times a2 n squared times a3 n cubed times a4 n to the a4 times n to the fourth is big O of n4. So this is an example just to illustrate the general property of polynomials, right? That the only thing that matters is the degree, right? The largest exponent. None of the constants matter. None of the low order terms matter, right? The proof, pretty trivial. Okay, this thing is at most this thing, right? As long as n is at least 1, a0 is no bigger than a0 times n to the 4. a1 times n is no bigger than a1 times n to the 4, etc. Okay, and then I can just take all the constants out front, right? Collect like terms. The sum of all the constants times n4. N to the 4 is an upper bound. Okay, and this fits our definition of being big O of n to the 4, right? Because this sum is a constant. Okay, so suppose f of n is 3n squared plus 17n times log base 2 of n plus 1,000. Which of the following is true? F of n is big O of n squared. Yes. F is big O of n cubed. Some people are less sure about this, but the answer is yes. So both A and B. And this is wrong. Why? Well, let's just do some plugging in here. 3n squared plus 17 is more or less what I've done before. Let me just pick something out of the air. So is more or less than, say, 3n squared plus 17n squared plus 1,000 n squared. So that's at most 1,020 n squared if n is larger than 1. I think we might need strictly larger here because of the law, but okay. So that's our definition of being big O of n squared, right? That's C is 1020 n naught. We'll call it 2. Okay. And this is less than or equal to 1020 n cubed. Also, if n greater than 1. Whoops. Okay, so this is showing it's big O of n cubed, right? Why? Because if n squared is an upper bound, so is n cubed an upper bound, right? Okay, so I used one kind of slightly odd property of the big O notation earlier and show that it's correct. So there's lots of properties that we want to understand so we can kind of use them very fluidly, right, when we're doing analyses. We don't want to always be messing around with these concrete choices of C and N naught. We usually want to just decide that there are such choices and quickly dispense with low order terms and such that are not interesting, right, in order to be efficient. Okay, so here's a bunch of properties. F is big O of F, whatever F is, right? Okay. If F is big O of G and C is a positive constant, then C times F is still big O of G. Why? There's a constant hidden in the big O, and you just make it bigger by C, right? To show that it's true. If F1 is big O of G1 and F2 is big O of G2, then F1 times F2 is big O of G1 times G2. That's just multiplying the things together and plugging them into the definition and letting C be the product of the two C's and N not be the max of the two N's. Okay, and it all works out. Sums, if F is big O of G1 and F1 is big O of G1 and F2 is big O of G2, then their sum is, okay, it's obviously big O of the sum of the G1s and G2s, but this is a little more convenient. It's big O of the max, and that often is convenient for throwing away low order terms quickly. Okay, in fact, it's what we did with the it's the short way of doing what we did with the polynomials, right? Getting rid of all the terms in the sum except the higher degree one. Transitivity, if F is big O of G and G is big O of H, then F is big O of H. These are all straightforward to prove. And so I'll leave that as an exercise, which you should all make sure you can do. Okay, now big O is a upper bound, okay? But we also need a lower bound, corresponding lower bound. Why? Consider this. So people say things like this all the time. Any comparison-based sorting algorithm requires at least big O n log comparisons in the worst case. Or I don't know what something else, yeah. Sequential search requires at least big O of n. Or something harder, linear programming requires at least n to the 3, big O of n to the 3. All these are meaningless statements mathematically. We usually know what the person means, but they're mathematically meaningless. Why? Because, let's just make that clear, right? Let f of n equal 1. Okay? F of n is big O of n log n. Okay? So all you've really said here is, okay, requires at least one comparison. I could argue you just said it at least 0, right? It doesn't say anything because this is an upper bound. It requires at least no more. This is saying literally at least no more than. Okay, it's not saying anything at all. So you want to say there's a lower bound, okay? And for that, we have big omega, the exact analog of big O, but to give a lower bound. Okay, and the definition is exactly the same. F of n is big omega of G of n if there exists positive constants C and n naught, such that f of n is at least, oops, let me take that back. F of n is at least C times G of n whenever n is bigger than n naught, okay? The only thing that's changed here is the direction of the inequality. It's changed from an upper bound to a lower bound, okay? So the intuition here is very similar. It's just the dual, right? So this is f of n, okay? And to say that f is big omega of g of n is to say that there's some constant so that when we take c times g of n, we get a function that's always smaller than f of n. Okay, maybe not always, maybe there's some small values where it's not the case, but right, except for some finite number of small values, it's always below f of n. That's a lower bound for f of n. And again, our constant serves this purpose. Maybe this is g of n, maybe g of n is never smaller than f of n, but I can multiply it by a constant that makes it a lower bound, right? In that case, so in this setting, c will be a smaller than 1, but larger than 0. Okay, so for example, let f of n be this function that we looked at before. Okay, so we'll claim f of n is big omega of n squared and also big omega of n, but it's not big omega of n cubed. Right, so a more correct use, or more correct way to talk about the lower bound is to say any comparison-based sorting algorithm requires big omega of n log comparisons in the worst case. That's a claim that there's no sorting, there's no comparison-based algorithm that sorts in less than some constant times n log n comparisons. Okay, now let's look at these two. Oh, we have one more thing to do. So this slide is, again, it's just like the one I gave you for big O, except it changes from upper bounds to lower bounds, right? So usually if I say algorithm as A is big omega of f of n, this is short for the worst case running time of A is big omega of f of n. Notice, so this is very important here. Students very easily get the idea that omega is somehow about best case rather than worst case. Big O is not about worst case or best case. Big omega is not about best case or worst case, right? Big O and big omega are ways to describe functions, right, by giving bounds, asymptotic bounds on them, okay? And which function you're describing is up to you, okay? So because in algorithm analysis, most of the time we're studying worst case run times, it's also the case that most of the time when I say algorithm A is big omega f of n, I mean its worst case time is big omega of f of n. Okay, so that's short for the same thing. Let t of n be the maximum number of steps the algorithm takes on any input of size at most n, and t of n is big omega of f of n. Okay, so what does that mean? It means there are these constants, okay, such that this inequality holds. T of n is bigger than some constant times f of n, except for some finite set of small values, right? Okay. For all sufficiently large n, or for all but finitely many small values of n, or maybe the nicest way to say it again is t is asymptotically lower bounded by f. Okay. So let's do this two examples. Okay. So we claim f of n is big omega of n squared and big omega of n. How do we prove that? Well, it's pretty simple, okay? So there's f of n, okay? It's obviously bigger than n squared as long as n is at least 1, okay? Right, and n squared is larger than or equal to n squared, which is the same as 1 times n squared, right? Okay, so that gives us choose c equal 1, n not equal 1, and that gives us our big omega of n squared. And n squared is obviously bigger than n, right? At least n, okay? So it's big omega of n, right? I mean, if n squared is a lower bound, surely n is a lower bound too, right? If it's proof of 2, it's not big omega of n cubed. Well, let's assume the contrary. Let's assume it is big omega of n cubed. Then there are two constants, okay, with the property that if n is bigger than n naught, f of n is at least c times n cubed. Okay, and now I'm going to reach a contradiction. Let's choose n to be the max of 50 divided by c and n naught, and add 1 to that. Okay, now when you go to do this, you're confused. How do you get this, right? What is this about? So let's just look at the parts. Okay, first, n needs to be bigger than n naught, because for values smaller than n naught, the definition nothing is said, right? Okay, and so I have a +1 to make it strictly bigger, right? And then I need to make it big enough that something goes wrong, right? Okay. So what is it? Well, the claim, which I'm disproving, is that f of n is always bigger than c times n cubed. So I need to pick an n large enough that this turns out to be false. And so I don't know what that is until I do it, right? So I'm just going to carry out the process. F of n is 32n squared plus 17n plus 1. Okay. And this is, I'm just going to add these things up, right? This is no bigger than 50n squared. That's just what I did in the previous analysis of this function. Okay. And I need that this thing is less than c times n cubed, right? Because that's what's here, right? Okay. And so I need to pick my n. Sorry, I need to pick my value of n so that this holds, right? So 50 is less than c times n, so that this step holds, right? I need 50 less than c times n, so I need n is larger than 50 divided by c, and that's how I got the 50 divided by c here, right? Okay. Okay, what's an equivalent definition of big omega? Well, if we look at this if we look here, go back here. Oh, sorry. Yeah, f of n is, I was mentally ahead on a different slide, but I'm not going to redo my video just because I make a few mistakes, right? Okay, so f of n is big omega of g of n, if and only if g of n is big omega of f of n. This is true. They are exact duals of each other. Okay, so the definitions look similar, but they're also exact duals, right? The only thing that changes in the definition is the order of the inequality. Okay, and so it's very straightforward to prove that that's the case. Okay, option B is f of n is big ohm of g of n if and only if there's this constant c's naught such that f of n is at least c times g of n. Okay, I'm ignoring these greater than zeros. They're only there so you can put it, so you know it's these functions are larger than zero, so you can put them in the denominator of a fraction. I think that's the only reason they're there. We'll just ignore that. Okay, so such that f of n is greater than or equal to c times g of n for infinitely many n. Well, this is actually not right. And the reason is our definition insists that it's for all n. Okay, so you can have it, the inequality hold for infinitely many n, but still fail for infinitely many n. All right, so a corrected version of this, let's see if I can pull this off. In real time. This is true, provided if I make a correction, okay? So we'll call this B prime. If I replace for infinitely many n for all but finitely many. And this version is true. Okay, so B is false, so they're not both, but A is true, so. Okay, so for an exercise, actually prove this. It's really short, but it still feels nice to do it. Okay, now sometimes we have matching lower bounds and upper bounds, and then we feel we know very well what some function is. Okay, and so we have a notation for that. We call that having tight bounds if we have an upper bound and a lower bound that match, that are asymptotically the same, right? And that's what this is. So f of n is big theta of g of n. We say if there's 3 constants, C1, C2, and N naught, all positive, such that C1 times G of N is less than or equal to F of N, which is less than or equal to C2 times G of N, whenever N is bigger than N naught, or at least N naught. Okay, so what is that saying? Well, this part just corresponds to the big omega of G of N definition, right? So that's the lower bound. And this part corresponds to a big O of G of N, right? The definition of being big O of G of N. So that's this part. And F is sitting here in between, right? F is sandwiched in between 2 multiples of G of N. So we know that asymptotically it grows exactly the same rate as G of N, okay? So here's an example. Our same function, 32n squared plus 17n plus 1. We claim f of n is big theta of n squared. Why? Well, we already showed it's big omega of n squared. That's this half of the, right? That's this part. And we showed that it's big O of n squared. That's this part, okay? So that gives us our big theta of n squared. Okay. I forgot, I don't know why they picked this. This is just 1. But the same as in the previous slide where we did that lower bound. Okay. And then so, but f of n is neither big theta of n nor big theta of n cubed. So when we showed the upper bound, so it's f of n is big O of n squared. It's also big O of n cubed. And it's big omega of n squared. It's also big omega of n. Okay, but it's not big theta of n or big theta of n cubed. Why? Well, because it's not big omega of n cubed, right? It doesn't grow as fast as n cubed. And it's not big O of n. It grows more fast than n, right? So there's no big O of n upper bound because it's theta of n squared, and there's no big omega lower bound because it's theta of n squared. It's big O of n squared, so it can't be omega n cubed. And it's big omega of n squared, so it can't be big O of n. Okay, so we might say something in use like this. In usage, merge sort does theta of n log n comparisons to sort n elements. Okay. Which is an equivalent definition of the big theta? Well, we basically have just been saying this, right? F of n is big theta of g of n, if and only if it's big O of g of n and big omega of g of n. That's exactly equivalent. Here's maybe a more interesting one. F of n is big theta of g of n, if and only if the limit as n goes to infinity of f of n over g of n is some constant c, just some constant c, that's larger than 0. Why? Well, if you think about this, it kind of makes sense. F of n is sandwiched between 2 different multiples of g of n, right? So the ratio of f and g kind of, does it make sense? Kind of makes sense, but we'll prove it. Okay, but this statement is not correct. So this statement is good. This statement actually is not quite correct. So we're going to show, I'm going to show one direction of this, right? Namely, this one. this one. Okay. If this limit, right, if this is true, then f is big theta of g of n, and we'll prove that on the next slide. But why is the other direction not correct? Because the limits might not exist, right? Okay, it can be actually that this is true, but the limits don't exist because these are wonky functions. Okay, so it's not quite true. It's almost true. Okay, so no. Okay, so let's prove this. Suppose that the limit as n goes to infinity of f of n over g of n is c for some constant c. We claim f of n is big theta of g of n. Why? Well, by the definition of the limit, for any epsilon larger than 0, there's some n naught such that the ratio is bigger than c minus epsilon and smaller than c plus epsilon. That's just the definition of a limit, plugging the functions in, right? Okay, whenever n is bigger than n naught. Okay, so now I'm going to choose a value for epsilon. I'm going to choose it to be half c. Okay, so I can plug that in. Okay, and I'll plug that in. I'll plug in epsilon, the value of epsilon for here. So what do I get? I get c minus half a c is a half a c, and c plus a half c is 3 half c. So I get two constants that I know. Okay, and I'm going to multiply by g of n, right? So I'll multiply everywhere by g of n. So I take out the g of n out here, and I put 1 in front here, and I put a g of n here, and I get this. A half c times g of n is less than or equal to f of n, which is less than or equal to 3 half c times g of n. That looks really familiar, right? That just fits exactly the definition of f being big theta of g. Okay, with those two being our c1 and c2 in the definition. Okay, so that's really some. So a little exercise to make sure that's clear. Prove the following. Okay, if the limit of that ratio goes to 0, f is big O of g, but not big omega of g. And if the limit goes to infinity, f is big omega of g, but not big O of g. Okay, now we're almost done this lecture. We'll just very quickly go through a few common running times, right? Big O of 1 means bounded by a constant. It doesn't depend on the input size at all, right? So things all kind of standard one-step programming things, conditional, an arithmetic or a logic operation, initializing a variable, following a pointer, accessing an ith element in the array, comparing or exchanging two elements in the array, et cetera, et cetera, et cetera. Okay, simple. Linear time means running time big O of n. Okay, all kinds of things. Sequential search, merging two sorted lists as done in merge sort, right? Because you visit each element in the two lists exactly once and copy it. Okay, I'm not going to go through the details of any of these. Logarithmic time means time big O of log n. Okay, classic algorithm that everybody knows that's log time is binary search. Okay. Now, so this one they call it linear. I can't even say a linear rhythmic time. Why can't I say it? Because virtually nobody uses it. I've been to hundreds of talks on algorithmic complexity and complexity theory, and I doubt if I've heard it 5 times. So people just say n log n. Okay, running time big O of n log n. You've probably seen a few sorting algorithms that are n log n: merge sort, heap sort, for example. Okay. Quadratic time means big O of n squared. So any kind of thing where you have two nested loops, each bounded by, each going over n elements, right? So Gale-Shapley is the obvious one, which we've looked at a lot. Okay, except that the n is not the size of input there, right? The n, so So just think, so this example is you have pairs of points and you have to run over. So you have points and you have to run over all pairs of points, right? The same kind of intuition, that's n squared. N cubed, well, here's one. We want to give an array of n distinct integers, see if there are 3 that sum to 0. So the naive way to do that is what? You just enumerate all the triples, okay? So naively, you have 3 nested loops. Each one goes over all n values, right? N choices for the first one, n choices for the second one. Well, n minus 1, n minus 2 choices for the third one. That's n cubed time. Okay. This problem is actually doable n squared time with a fairly simple algorithm. We're not going to talk about it, at least not now. Okay, polynomial time means big O of n to the k for some fixed k, some constant k bigger than 0, right? So an example is find an independent set in a graph of size k. What does that mean? An independent set is a set of vertices that have no edges among them. Okay, so the obvious algorithm is enumerate all sets of k nodes. And that's not hard to do. And how many are there? Well, there are n choose k. And n choose k is bounded by n to the k over k factorial. And k factorial is a constant here, right? Some constant k. Okay, so this is big O of n to the k steps. An exponential time typically is thought of as something like 2 big O of 2 to the n to the k for some constant k. Okay, so 2 to the n or 2 to the n squared, maybe 2 to the n cubed. Okay, so the general independent set problem. So here we looked at independent sets of some fixed size, constant size, and the general one is might be find an independent set, find the largest independent set in the graph. Okay, so the naive algorithm is enumerate all subsets of n elements. Okay, how many subsets are there? About n factorial. Okay, and so no, that's not right. So consider each vertex can be in or out of the independent set, right? Okay, so you have 2 to the n subsets, right? So you have to generate each of those 2 to the n subsets, and for each one, check if it's independent or not, right? So you have 2 to the n subsets and something like n squared steps to check all pairs in one of those subsets to see if there's an edge or not. Right? Okay, and that's where we're ending for tonight, or tomorrow morning, or this morning, depending on when you're watching.